Namaste, mere pyare bachcho. Welcome back to our exam prep series. I know, exams are just around the corner, but don't you worry one bit. Today, we're going to master the chapter on waves, and I promise you, we'll make it super simple.
So, what's on the menu today? We'll start with the basics. What are waves, really? Then we'll look at the two big types you need to know. After that, yes, a little bit of math, but trust me, it's not scary. We'll figure out how fast they travel, what happens when they meet, and then we'll end with something super cool called beats. Sound good? Let's do this.
Okay, let's get right into it. Section 1. What are waves, really? Now, when you hear that word wave, you probably think of the sea, right? But in physics, well, it's a much bigger idea.
So here's the official definition. A wave is basically a moving disturbance. It's energy on the go. The classic example, and it's the best one, is dropping a stone into a quiet pond. You see those circles, those ripples spreading out? That's the wave. But now, think about this. If there's a small piece of cork or a leaf floating on the water, does it travel with the wave to the shore? No, right? It just bobs up and down, right there in its own spot.
And that, my dear students, is the most crucial point. This is a one-mark question, for sure. Waves move energy, not the stuff they're traveling through. The matter, the water, the particles of a rope, they just jiggle up and down or back and forth. It's the energy that's actually going from one place to another.
All right, brilliant. So now that we know what a wave is, let's look at the two main types you'll see in your exams. Super easy to tell them apart, I promise.
Okay, so it all comes down to one thing, direction. For transverse waves, the particles dance up and down, which is perpendicular to the way the wave is moving forward. Just think of wiggling a rope. But for longitudinal waves, the particles push back and forth, parallel to the direction of travel. A perfect example is sound traveling through the air.
And these diagrams, you'll recognize them from your textbook. They show it so clearly. Look at the left, the transverse wave. See that little red dot? It's just moving up and down. The wave moves forward, but the dot stays in its lane. Now on the right, the longitudinal wave. You can see the particles bunching up, that's called compression, and then spreading out. They're moving along the same direction as the wave.
All right, section 3, the math. Now, deep breaths, everyone. I know sometimes seeing an equation can be a little scary, but please, don't worry. We're going to break this down together step by step, and you'll see it's actually not that bad at all.
So this is the big one. This equation is like the heart of the chapter. It might look a bit intimidating, but all it really does is tell you the height or y of any part of the wave at any moment in time. You give it an x, where you are in the wave, and a t, what time it is, and boom, it tells you the displacement. Let's unpack what all those letters mean.
Okay, bachcho, screenshot this slide right now. This table is pure gold for your exams. They will give you an equation and ask for these values. A is amplitude. That's just how high the wave gets. K is related to the wavelength, and omega is related to the time period. You absolutely have to know these.
Okay, talk is cheap, right? Let's put this into practice with a real question. This one is straight from your textbook, example 14.2, so pay close attention.
And there we go. See how simple that was? Step 1, just look at the equation and match it to the standard one. Right away, you know A, K, and omega. Step 2, plug K into the wavelength formula. Step 3, plug omega into the period formula. That's it. Easy marks, Bacho. You can totally do this.
Awesome job with the math. Now let's move on to the next big question. How fast do these waves actually travel? What decides their speed?
Okay, another huge exam tip right here. The speed of a wave depends only on the medium it's traveling through, not on how big the wave is or how fast it's wiggling. For a string, it's about how tight it is and how heavy it is. For sound in a gas, it's about the gas's properties. You can't make sound go faster by shouting louder, can you? The medium is like the road, and it has a fixed speed limit. The wave is just the car traveling on it.
Okay, this is where things get really interesting. What happens when two waves meet? Do they collide like two cars? Do they bounce off each other? Nope. They do something much cooler. They just add up.
This is called the principle of superposition. It sounds fancy, but it's super simple. At any point, the total height is just the sum of the individual heights. If one wave says go up 2 and another wave at the same spot says go up 3, the result is go up 5. Simple as that.
And this simple idea of adding up leads to something we call interference. When two peaks meet, they combine to make an even bigger peak.
That's constructive interference. They're building something bigger. But if a peak meets a valley, poof, they can cancel each other out completely. That's destructive interference.
And where do you see this? On a guitar string. When you pluck it, the wave travels to the end, reflects back, and interferes with itself. This creates these amazing patterns called standing waves. You can literally see parts of the string that are totally still, those are the nodes, and parts that are vibrating like crazy, the antinodes.
All right, we're on the home stretch now. Our last topic, and it's a really cool one, you can actually hear. It's a direct result of that superposition principle we just talked about. We're going to talk about beats.
I bet you've heard this before. You know when someone is tuning a guitar or a sitar and you hear that wah-wah-wah sound? That is beats. It's what happens when two sounds with slightly different frequencies mix. It's just interference again, getting louder, then softer, then louder, then softer.
And the math for this? It's the easiest thing in the whole chapter. The beat frequency is just the difference between the two original frequencies. So if you have one sound at 442 Hz and another at 440 Hz, you'll hear two beats, two wah-wahs, every single second. Simple.
And to wrap things up, I want to show you something truly incredible. This is from our own country, from Tamil Nadu. These are musical pillars. Our ancestors, centuries ago, used the very same physics of waves and vibrations that we just studied to create pillars from stone that sing when you tap them. How amazing is that?
So, what's the big idea here? Waves are not just some topic for your exam. They're literally everywhere. The light from the sun, the sound of my voice, the Wi-Fi that's bringing this video to you, it's all waves. So yes, revise the formulas, practice the problems, but also just look around. See the physics in your daily life. You're gonna do great in your exams. All the best, Bacho. Now go and ace it.